Hello everyone. Now let's see the graphical representations for non-ideal solutions. In previous class we discussed about the graphical representations for ideal solutions and some examples for ideal solutions I was given. Now let's see what is a non-ideal solution. Non-ideal solution. How a particular solute in a solvent we have to consider as non-ideal. Suppose if particular solute is undergoing either dissociation or association, then we call as non-ideal solutions. So how they are showing from deviation from ideal behavior, let's see. So very simple, this non-ideal solutions are showing two types of deviations. One is a positive deviation from ideal behavior, and negative deviation from ideal behavior. So you have two types of deviations. One is a positive deviation from ideal behavior and one is negative deviation from ideal behavior. So when we consider a solution is showing positive deviation, very simple, the force of attraction or intermolecular attractive forces or force of attraction. Intermolecular force of attraction of AA and BB are greater than intermolecular force of attraction between AB molecules. So here what I am telling you is intermolecular force of attraction between AB are weak. The weak intermolecular force of attractions you have. Okay, the particular solute if dissolved in a solvent, if the intermolecular force of attraction between AB are weak, then those kind of solutions shows positive deviations. In previous for ideal what I told you, the intermolecular force of attraction of AA and BB means both solute and solvent is equal to intermolecular force of attraction between AB in what? Solution. So very simple, these A and B hates each other, then they show positive deviation. This A is a solute, B is a solvent, both are hating each other to combine. Then suddenly what happens? They show positive deviation. The same here you can understand delta V is greater than 0. Definitely, because intermolecular force of attractions are weak in solution. So delta V is greater than 0 for positive deviation. In same manner you can say here by using a small diagram. Here you have Mr. A. In ideal solute and non-ideal solute both are not same. This is different. And this is A. And here I have some solvent I have. This is solvent B. And these two was mixed. And you have a solution. Intermolecular force of attractions are very less in AB. Here you have Mr. AB. Here you have only A. Here you have B. Here they have more attractions. Here they have less attractions in AB. So they will spread. If they spread, here this is V2 and here this combinedly V1. So what exactly delta V? So for this delta V is equals to, definitely final volume is more. So V2 minus V1 final volume. So delta V is positive. positive. So delta V is greater than 0 for whom the particular solutions which having non-ideal solute and shows positive deviation. When positive deviation happen means if the intermolecular force of attractions of AB means solutions is weak when comparatively this force of attraction between A and B. These are very important. Delta V is greater than 0. Got it? And same, come to the negative deviations. What exactly negative deviations? See, same exactly but reverse. Okay? So intermolecular force of attraction of AA and BB are less. Now, in individuals these are weak. Means after formation they have a strong attraction. Means individually AA, individually BB have less interactions, but the intermolecular force of attraction between AB is very strong. You can easily identify if they have both solute and solvent has ability to form hydrogen bond like that. You can give examples for a negative deviation. The solution which show negative deviation means between solute and solvent you must have one particular strong bond like hydrogen bond. Suppose ethyl alcohol C2H5OH in water. This solution shows a negative deviation. Why this will show negative deviation? Because individually ethyl alcohol I am considering AA, water B. Okay. After mixing this ethyl alcohol mixed with water, we know it's highly useful. Correct? So ethyl alcohol when dissolved in water, certainly they have a strong bond. If they have a strong bond, strong interactions, volume what will happen? Decreases. The final volume will be less. After formation of solution, volume will be less. So here the delta V will be less than 0. Here delta H also less than 0. That means exothermic. Delta H negative less than 0 means because after formation they have strong bonding. So delta H is less than 0. But whereas here for a positive deviation who are showing that is delta H is greater than 0. Delta V greater than 0, delta H greater than 0 for solutions who show positive deviations. A final conclusion I will write here. Delta V is greater than 0, delta H greater than 0 for positive deviation. Delta V is less than 0 and delta H is less than 0 for the solutions who show negative deviations. Okay, so this is about the non-ideal solutions, how they are showing positive deviation as well as negative deviation. Now let's see the overall graph for positive deviation as well as negative deviation. Just have a look everyone. The non-ideal solutions are showing two types of deviations. One is positive deviation and one is a negative deviation. When the positive deviation happened, here I was given, I won't waste time. When the negative deviation happened, I was given. For the positive deviation, this is about delta V and delta H, and for the negative deviation, this is about delta V and delta H. Okay? Now just follow me. Follow me means how to give the graphical representation for a non-ideal solution. So non-ideal solutions are, as I told you, they are showing a positive deviation as well as a negative deviation. So how that deviation you can represent in graph. So now our thing is graphical representation. So graphical representation of or for non-ideal solutions. Graphical representations for non-ideal solutions. Let's see. So first, let's discuss about positive deviation graph. Positive deviation. For positive deviation, what I told you, intermolecular forces between solute and solvent are weak. Certainly, if they are weak, if you heat, they will evaporate fast. I was given factors affecting vapor pressure. That's why I was given. If the intermolecular forces are weak, certainly they can evaporate. Okay, so I am talking about solution. Okay, so solution having weak intermolecular force, vapor pressure will increase. So here for what exactly the graph? Let's see. Let's see here. You have the same story. Here this side you have Mr. This side you have Mr. mole fraction of A, which is 0, and here mole fraction of A is 1, and here you have mole fraction of A is 1. So here you have PA naught. Here in reverse manner, here mole fraction of B is 0 because total is always 1. Here the mole fraction of B is 1. So as I told you in previous, same story. Here you have some 0.2, 0.4, 0.6, 0.8, 0.2, 0.4, 0.6, 0.8. Mole fraction of A is increasing, so the graph is like this. So here you have some PA naught. Okay, so here the mole fraction of B is reverse 0.8, so it is 0.2, total is 1, 0.6, 0.4, 0.4, 0.6, 0.2, 0.8. So in this way, the graph is increasing in this way. So you can draw a graph like this. So here almost, here you have Mr. Actually great artist, but so here you have Mr. PA naught, and here it is what exactly here here. So this is P total. It is equals to PA plus PB. See the diagram, great artist drawn. And this is vapor pressure, and here you have mole fractions. If you want, I will write mole fractions. Whose mole fraction? Solute. Both solute and solvent. See here. The gas is showing a positive deviation. So from this, when positive deviation happens, definitely the vapor pressure will increase because in solution they have weak interactions. So the graph will be like this, positive deviation. Positive deviation you can mention like this for P total everything. This will increase. This is for ideal actually. The straight lines are for ideal. The straight lines are not for non-ideal. Okay. This one is deviation. Positive deviation means above you have to draw like this. Means showing a positive deviation like this. So this is the graphical representation for the solutions who are showing positive deviations. See, Actually the straight line is for ideal. I am repeating. This black color, this graph, this straight line indicates what? Ideal solution. This red color, this red color, this red color, those indicates they are showing positive deviations because vapor pressure will be somewhat more than expected. Got it? So it will be experimentally it will be more. Yes, it's more coming like this. More. So this is about the gases who are, the particular liquids who are showing positive deviations when they have non-volatile solute. I hope you understood about a positive deviation graph. This is a positive deviation graph. And who show positive deviations? Who show positive deviation means some C2H5OH in acetone. Do you know acetone? CH3COCH3, acetone. So this is example for the solutions who are showing some positive deviation. C2H5OH in acetone is showing positive deviation. And like this, CH2 in acetone. I am telling you, these both hate each other. Ethanol in acetone hate each other. CH2 in acetone hate each other because here O minus you have, here S minus you have, and like some polar and it is non-polar. Of course, it is a non-polar completely, but individual bonds are polar. That's why it hates acetone. Individual CS bond is a polar, so they will hate acetone. And this C2H5OH is like a polar and acetone is a non-polar. CO minus and acetone is a non-polar. They hate each other. Both are like non-polar, ideal. Just simple logic, simple trick I am telling you here. And one is polar and one is non-polar, they hate each other. Like that. Okay? That polar dissolve in polar, non-polar dissolve in non-polar, like dissolve like rule we have. Got it? So like that. Who show negative deviation? I was given already example. Ethanol in water. So they have attraction after combination. After combination they have attraction. So they show some negative deviation. So what is the graph for negative deviation? Let's see. Same thing, same story. I will write here some negative deviation, how they are showing. Otherwise I will write one more time, not a problem. So graphical representation for solutions who are showing negative deviation. Negative deviation from ideal behavior. So that you can draw a graph like this. Again same story. So you will have like this. And here you have mole fraction of A is 0 and here mole fraction of mole fraction of A is 1, here mole fraction of B is 0, here mole fraction of B is 1, in middle like this, ding 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 like this. And here it is 0.2, 0.4, 0.6, 0.8. Don't feel bored, you have to understand all this, very very important. And it is 0.8, 0.6, 0.4 and 0.2. In this way mole fraction of B is increasing. So as I told you, this will be the thing you have to remember. Okay, and this is P total and this is PA naught and this is PB naught and this is P total. P total is equals to PA plus PB. So here this is PA and this is PB. For negative deviations, after formation of a solution, they have more interactions. So volume what happened? Decrease or increase? Volume decreases for resulting solution. So for this, that's why I told you this delta V is less than 0 I told you. Means volume decreased after formation of a solution. So A plus B combines to form AB. To form AB. Here what you have, here the interactions are less. Here the intermolecular forces are more. Intermolecular force of attraction are more. So volume what happened if intermolecular force is more? So volume decreases. Final volume will decrease. So it will be negative, like delta V will be negative. Means more intermolecular force of attractions means you need more temperature to heat. So certainly vapor pressure will decrease. Because vaporization will decrease because they have more intermolecular forces. I was given factors, I am repeating. Okay. So here intermolecular force of attractions are more in solution. Certainly they cannot vaporize easily. Certainly the vapor pressure will decrease. So now the graph will be downwards like this everywhere. So this PA graph will be like this, downwards. In previous upwards, now you have downwards like this. And this will be downwards. And this also downwards. So red color what I am showing is for negative deviations. And this black color exactly ideal. Okay. This much is the deviation. This much is the deviation from ideal behavior. And here you have a deviation from ideal behavior. And here you have a deviation from ideal behavior like this. Means this much of area is a deviation from ideal behavior because they are showing negative deviation. I am repeating, negative deviation when happen means the intermolecular force of attractions in solutions are high than intermolecular force of attractions in individual solute and solvent. So these are about the Raoults law. Raoults law one by one, if you see last few minutes I'll tell you. So few things we discussed, like Raoults law means what, when non-volatile solute if present, what happened I told, I won't repeat all those things. And that partial pressure or vapor pressure is directly proportional to mole fraction. So that relation we have, like P total is equals to PA plus PB, or P total is equals to PA naught Xi A plus PB naught Xi B like that. And afterwards I was given ideal and their graphs, and previously how to calculate mole fraction of particular solute and solvent in gas phase or vapor phase I was given. And here I was given deviations from ideal behaviors. One is positive deviation and one is negative deviation. And here negative deviations who show I was given, and that example suppose C2H5OH ethanol in water. You can check some more examples in our material as well as our textbooks. Got it? Thank you. So next we have a new concept regarding solubility of gas in liquid. So that is our concept. Solubility of gas in liquid. So what factors will influence the solubility? What factors will influence the solubility of gas in liquid? Let's see one by one. Suppose nature of gas. Nature of gas. Suppose if the gas I am considering HCl, H plus Cl minus, I am dissolving in water. So this gas is what? Polar gas. HCl is a polar, water is a polar. So like dissolve like. So this HCl is a polar, so water is a polar, so this can easily dissolve in water. Like dissolve like. So final conclusion, if gas is polar, that can easily dissolve in polar solvents. If gas is a non-polar, so that will dissolve in non-polar solvents like that. Getting what I am saying? Like, dissolve, like. Same in this O2, N2, some H2 gases. These are somewhat less soluble. Very much less. Why? What is the reason? What is the reason behind it? Because these are non-polar. That is the thing. Solubility depends on nature of gas. Solubility of gas depends on what? Nature of gas. What is that? Whether the gas is polar or non-polar. That also influences the solubility. Solubility means what? I was given how much solute is soluble in a particular quantity of solvent. Solubility formula also I was given in previous. Solubility is equals to weight of solute by weight of solvent into 100. This formula I was given in previous for solubility. So solubility how influenced